There you go. Cool. Which one? Sorry?
18.
Oh, yeah.
Yeah.
18 and 3/9? The baseball diamond?
Yeah.
Okay. Alright, this one's got baseball diamond. Alright, that's the diamond. Good job. Throw it down. There's home plate. It's 90 foot on the side. Where'd it go? The batter hits the ball and runs towards first base with a speed of 24 feet per second. At what rate is his distance from second base? Oh, you like it already. I know.
Second base.
At what rate? So let's say he's right here. Woo-hoo. There he's going. He's going. Let me put some indication of which direction he's going. He's going that way. All right. That's the arrow. And here's second base, of course. So the distance from second base to this dude. Let's just make second base this point. Right. We'll make the dude this point. Right, and what do you want to call that? I obviously have to give that a name.
Z.
Who?
Z.
Z. I love it. Kick ass. Z. And they say that, and what do we want to call this? And this velocity relates to what?
Him moving from home plate to first.
Yeah, so it could either be the speed at which this is changing or the speed at which this is changing, because they're both the same, right?
Yeah.
If he's going away from this, he's going towards us at the same speed, just, one would be negative possibly. Let me stop there for a second. And your choice on that doesn't really matter, but it changes how you draw your triangle. So I don't know, did anybody do this? Did you choose a place to describe? Did you describe this one? It seems to be a nice one because this is a nice right triangle. This is 90 here, right? So if you say this is the distance, so let's call this what? I'm going to call it X, I guess. All right, good, we agree. So that's the distance away from first base. All right, let me stop there for a second.
You're not home. So shouldn't it be 90 if you're starting from home?
What do you mean?
No, because he's out.
No. So again, you have these, what's a good word? These set measurements of something. But then when I'm filling a cup, the water level is not all the way to the top. When I'm running the base, I'm not this far away from that base, I'm this far away. Well, how far away is that? I don't know. That's because I don't know where the dude is.
Well,
aren't you starting from home now?
Totally are.
So
he's asking when he's halfway there.
Oh yeah, so we'll get there.
So it's clear.
So you guys, we have to set up. If you think too much about a specific instance, then you're going to start putting numbers in too early. Your derivatives will all be zero, and you what the hell's going on? I know he's moving, so it can't be zero, right? So I have to be as arbitrary as possible. So even if they said you have a cup that's conical and the water level, and I want to know what's the rate when it's halfway, I'm not going to use that. I'm going to use variables to describe some arbitrary position. So he totally is starting here. But I'm just going to represent him somewhere on his run. Because whatever relationship I come up with has to hold throughout this whole time. And if I put him here, I might get too excited about using this. I can't use this because that's changing. That's not constant.
So would this be like x squared plus 90 squared is equals z squared?
So now that we've got this beautiful little triangle set up, and I really want you guys to understand, why did I draw this line? Why did I draw that line?
Because we need another side to the triangle.
No. Not just that. Because that's the question. Right? At what rate is his distance from second base decreasing? Okay, so I need a line that represents his distance from second base. You guys semi with me? It's always, what's most important in the problem, I'm showing you what to do is, why did you do that? Why did you choose that? Listen, that's the question you want to be asking. I'm like, oh shit, I don't know. So that was the question they asked me. And then why did I give this a variable? Because what the hell is this?
That's the rate. So then we
Now I can call it what?
dx over dt.
Dx dt, because I gave this a freaking variable, right? Of course it's a variable, because they gave me a rate of how it's changing, didn't they? So he's running towards first base. Obviously, he's getting closer to second base. Are you guys cool with that? So obviously, his distance from second base is decreasing somehow. Okay, so dx dt. So if you really want to be precise, this distance is decreasing, so you can say that this is negative 24. Okay, maybe.
So would you go to diagram and then?
Yeah, like Mike said, this is a right angle, so this is a nice right triangle. So then the relationship between the thing I know something about, the thing I want to know something about, and some constants or whatever, is
x squared plus 9 squared is equal to z squared.
good. Because that's the hypotenuse, kick ass. And that's the equation that you can now attack with derivatives.
So, would you attack with derivative and then plug in 30?
Where's 30 coming from?
Because
Oh yeah, I'm sorry.
I mean 45.
45, so halfway. Yes, exactly. Totally. Because you can't, if you put a specific number in for something that's changing before you've taken derivatives, that piece is going to go to 0, and really it shouldn't.
Yeah.
Yeah.
So would putting for the x part, if you put 90 minus x, would that make it like we shouldn't do that?
You could, but it's sort of like the other day when we had the shadow, we were trying to figure out what would make it easier. It would still work.
But don't you have to solve for z though?
Yeah,
Before we can do it?
Yeah, after you take the derivative.
Oh, at this point, it doesn't matter what you do with that equation. I mean, if there's something you can do to simplify it to make it easier to look at,
But I mean, you're going to be left with 2z dz over dt, so...
that's fine. What's wrong with that? All right, let's keep going. You guys are so some of your concerns will be addressed once you start to do the problem. We've got enough to do something with, right?
Yeah.
You guys are too worried about what do I do next. Well, finish what you got in front of your face first, and then bring in what we haven't brought in yet. That they're interested in the halfway point, and then see what that means. But don't bring it in yet. You're being too specific then.
But
Don't.
I'm just concerned because if we're going to solve for dz dt, we need to know z though.
Let's get there. I don't have that yet. Let's get there, and then we'll worry about it. So what do I do here?
We have the
0.
Good.
2z dt.
I like it.
Divide by 2z.
So I need to know x. And what am I going to put in for x?
45.
So I'm not sure why you guys are so worried about what to put in for z. I really don't understand. So at the point, so that's the general relationship between, and of course the 2's go away, whatever. That's the relationship between these two rates, right?
Would just be the square root of 45 squared plus 90 squared.
Let's catch up. What point are they interested in? The halfway point, right? So let's draw a triangle that represents that point. So what's this distance here going to be?
45.
45. And what's this distance here going to be?
That's going to be the hypotenuse. Z.
Yeah, and you can figure out what it is, can't you? Because you have two other sides.
Yeah, but then you should have plugged in 45 originally in the parabola. Put that here in on this.
No, you would have got the
Hell no. Hell no. Because,
How are you going to find z then?
why was I allowed to put the 90 here? Because as he's running to first
But
base,
90's
is this changing?
No, exactly.
Beautiful. So why would I put 45 here? That's too specific. X is changing as he's running.
But you still, how are you going to solve then?
Because
How you
I
gonna
don't
find
understand. What is X at the point when he's halfway to first base? 45. What is Z?
Z?
No. What is it?
I don't know.
Figure it out. You got a right. You got a right triangle. How many sides do you know? 2 of them. Can you figure out the last side?
And it's Pythagorean then. So I
It
can
is.
just plug in.
I don't understand.
Because if you have a constant of...
Oh, so if you want to do this first and remember that it's going to happen later, who cares? Now I understand your problem. You didn't mean to plug it in here and then take derivatives.
No.
You meant plug it in and figure it out.
Yeah.
You could do that first if you wanted to. I just wanted to do this first to see what I really needed. And then I go, oh shit, I do need Z. Now let me go back and do it. So you'll do it first and you'll have it. That's awesome. I don't care. All I need to do is I need to get this equation and I need to get the values at the time that they mentioned. I don't care which one you do first. I'm just worried if you do this first, you start putting stuff here that makes your derivatives all come out to 0. Yeah.
How come dxdt became negative 24 from r? Is that what it said, r?
Well, this is velocity. This is velocity, right?
Okay.
And that's just they didn't even call it v. They just said at a speed of whatever. So it's really speed. Doesn't really depend on direction. So now I made it more specific with the variable that we chose.
Okay. Okay.
Velocity is the rate of change of that side, and we call it x. So it's dx dt.
Okay.
Cool. So you see how important notation is to mathematics. You could call that side whatever the hell you want to, but you got to be consistent with it. So you give it whatever name you want to. So now I can figure out what z is. Did you do it?
No, I didn't.
Oh man, I thought you would have done it since you kept saying you should have done it.
And the square root of 45 squared plus 90 squared.
Yeah, that's what it is. Does anybody have a calculator?
100.623.
Say again?
100.623.
100.623. Sounds about right. So the 2's go away. You plug in x of 45. You plug in z of 100.623. You plug in negative 24 for dx dt. And again, the negative doesn't really matter. I like the way in the problem they say speed. And speed does not care about direction. So even if you didn't put a negative, you would get an answer. This is the right answer. It would just be decreasing. Or you put a negative in to be very upfront about it's decreasing because I see a negative. Right? Either way, it doesn't really matter. Okay. So some looks of concern. That problem's basically done. I didn't want to do any more because it's basically done. I want you guys. Now it's just plug and chug. That's all you got to do. That's part A anyway.
Part B is the same thing.
Part B, yeah, part B, you do everything. You just set up a triangle from third base. And the funny thing is, if you really realize what's happening at the rate at which he's going towards second base has to somehow be related to the rate at which he's going away from third base. Yeah.
Well, couldn't you just relate it to the same rate that we used for the first one?
Well, you could redo the whole problem and set up a triangle.
Yeah.
Or you could realize
You could realize.
more basic truth. Yeah, but anyway, either way, you'll
the
get it.
obvious answer.
And question 40 was also fun.
40?
Yeah.
Oh yeah, the island problems are always nifty. Oh, is that the one with the sweeping? No.
Yeah, like the light moving.
Moving along the shoreline. Okay, I got you. Whoa. It's too bad it's not the one I need.
An old man, a bicycle, and a balloon.
Yeah, I was trying to figure out what the bicycle. I thought maybe it was a wheelchair. I don't want you guys to get too jealous of somebody who can write well. Okay. So this problem, number 40. So a lighthouse is on a small island 3 kilometers away from the nearest point P on a straight shoreline. So here's the island, the lighthouse, shoreline, 3 kilometers away. Its light makes 4 revolutions per minute. Interesting. Blah, blah, blah. How fast is the beam of light moving along the shoreline when it is 1 kilometer from P? So this is P here. This is the nearest point on the shoreline. And notice they don't say which side. Doesn't matter. So the light, you can imagine the light comes in and sweeps through, right? And it comes around, sweeps through again, and you're like, oh my God, I got to blacken my windows so I can get some sleep. So at a point when it's 1 kilometer, and I'll just presume it's on this side, it doesn't matter which side. So let's say this is 1 kilometer, it's shining right there right now. And it wants to know how fast, where'd it go? Moving along the shoreline, how fast is this distance changing at that point? So we got a nice shape that's developed already.
Yeah.
Is that helpful? And this relates to what
Is
exactly?
that the rate of the angle?
Good. It's related to the rate of the angle. I like it. I don't know if you guys realize it. So 4 revolutions per minute. Maybe revolutions is not the best. What am I trying to say? Units to have it in, but it all depends on how you do this. So,
are you saying that you would change the revolutions per minute to theta or some angle?
well, we'll see if it becomes a problem.
Okay.
It's something to keep in mind is the units are not something we're used to using. Probably going to become a problem, or maybe we'll see.
Are we gonna use tangent of theta?
Yeah. So what relates these two things? Because these are the things I'm interested in, right? And in fact, you got to be careful. 3 doesn't change, right?
No.
But this is a specific time. So really, what I want to call this in general, that's crazy. All right. So then what they tell me is d theta dt, right?
Yeah.
And what they ask me for is dx dt, because that's the shoreline, right? How quickly is this changing? That's dx dt. So this is not the only way to set this up, but I'm trying to think of other ways, and they're basically the same thing.
That's not a right triangle, is it?
Yeah, why is that a right triangle? Why has it got to be a right triangle?
Because it's a straight shoreline.
Straight shoreline, and that's the closest point to this. So the closest point on a line to some point has got to be on the perpendicular to it. You don't have to get it too deep into theorems. It just kind of makes sense, right? So that's definitely going to be, thank God we don't have to use law of whatever. Those derivatives, related rates with those, but it might happen to you sometime. Sorry. So what they're asking me for is dx dt. All right, so then what's the, like you said, the relationship, what's tangent theta would equal what?
Yeah, 3 x over 3.
Yeah, it would be x over 3, kick ass.
And then take the derivative.
So x, just to get the 3 out of there so it's a little cleaner. Or it doesn't matter if you do or not, it's just a constant, it just travels wherever it is. Take your derivative.
So that'll be
And you eventually, so let's work with this for a second. What is the units that I want on my theta? To be careful, in general, radians. And this will have, anytime, if theta is inside of a trig function, it doesn't matter. It doesn't matter. Because it would be the sine of a representation of an angle, and sine just cares what the angle is. However you want to call it. So if you call a 45-degree angle Fred, then the sine of Fred is rad 2 over 2. So the sine doesn't care. But if it's not inside of a trig function, then math will go, what the freaking hell is Fred? So we better represent it with radians. That's the real unit measurement, right? Radians are real measurements. Degrees are made up shit. We like the number 360 because we can cut it in a lot of different ways. And we actually kind of stole it from the Babylonians, to be honest, but you know, they weren't around to worry about it. So
how would you change 4 full 360-degree terms?
what's that?
Yeah, how would you change 4 full 360?
Yeah, so what's 1 revolution? How many radians is 1 revolution? 2 pi. So how many radians is 4 revolutions?
No, 5 or 2.
1 is 2 pi. 2 is 4 pi. So 4 is 8 pi. So 4 revolutions equals 8 pi radians. So 4 revolutions per minute is 8 pi radians per minute.
Okay.
Is that cool?
Yeah. So now you can attack it, right?
Now you can attack it. Now you can fully just attack it.
That's, I feel like the majority of the problem is just that,
Yes, as always. The minute you get it set up, the equation should just flow off of it. And the minute you get the equation, the derivatives should be relatively simple. Just got to do the chain rule stuff right.
The last one has 3, 4. And then figure out the last 2.
All right, so now 44, and then I'll see what. Is that one of your questions?
No, I had a question on from the previous one. Like,
This guy?
I did not understand why did you use tangent?
So this is.
Yeah, I know it's opposite of reducing, but isn't opposite one?
No, be careful. This 1 is that it's just like the 45 from last time. It's just like the halfway. That's a specific time. So this is changing constantly. So I need to first figure out what the relationship is between this rate of change and this rate of change. And then I can plug 1 in for x to see what it is then, right at the point when x is 1.
Oh.
So I cannot plug that number in here, because then I get 0 equals and there's nothing to work with.
Okay. Yeah,
All right.
So the adjacent angle is x.
Sure. I forcefully keep SOHCAHTOA out of my brain, so it's up to you to know. Me, that's in the base, so tangent is y over x, right? So it's x over 3. It's the y piece over the x piece.
Oh.
Yeah, so whatever way you like. I don't know.
So then you take the derivative and then just put the 8 pi for theta.
Yeah, now you know that this is your d theta dt. Careful. That's your d theta dt. What is that? Am I going to have to know a value of theta?
no.
Well, think about it. Yes, you will. But you know, again, we did one the other day. I don't have to get down to the theta level of things. I just need the sides of a triangle.
Wouldn't it be 1/3 then?
Well, no. When you take the derivative, you're going to get
Oh, secant. Never
secant,
mind.
and then you can figure out the secant. Yeah. Which is going to require this side, which is easy.
Yeah.
All right, maybe. So we looked at one like that yesterday. Don't get all the way down to figure out what theta is. You normally don't need to. You need to know what secant theta is or something like that, and that's just ratios of sides of triangles. That's easier to get a hold of. It's a much better looking number. Okay, all right. So 44, 2 people start from the same point. They have a big argument, and one walks east. I might have embellished there. One walks. I always try to come up with why things are happening in a problem. One walks east at 3 miles an hour, and the other one walks northeast. Of course, northeast. Why not? So northeast, which means what's this?
Not 90.
What did you say? Not 90? I like it. This is 2 miles an hour. Who is it?
45.
If this is east and this is northeast, this must be 45 degrees. That's the
That makes sense.
definition of 45 degrees in one way.
That makes sense.
Or the definition of northeast, that's even better. Blah, 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 blah. How fast is the distance between the people changing after 15 minutes? So what you do is, take this out, you take this out. Some arbitrary point. There's the distance between them, right? You draw in the distance between them. Now, is this necessarily... Now, this is interesting. I've drawn it sort of like it was a right triangle there for a second, but is it necessarily?
No.
Because he's going faster, right? So I don't know. There's some arbitrary time. Do I know that's a right angle? No, I don't. Ooh, I like it. You guys understand? If they were going at a certain speed, then they could make a right triangle at a certain time, but even then, the minute they go a little further, it might not be a right triangle anymore. Okay. So, this is going to be interesting. How fast is the distance between the people changing after 15 minutes? So, what do you want to call this?
Z.
That's awesome. What do you want to call this?
X.
Sure, man. And this, I guess, is going to be... Did you say Q? Alright. I was hoping you would say something freaky. Doesn't matter. What you call it? ABC.
So do we have to change our rate?
Do what? I'm sorry?
Do we have to change our rate? Because it's in minutes, right?
Well, you just got to realize that 15 minutes is how much of an hour? Yeah, 1/4 of an hour, you're all good. But yeah, you've got to be careful. Don't put 15 in thinking it's hours or something. Yeah, 15 times 3, they ain't going that far after 15 minutes. So it's 1/4 of an hour times 3, 1/4 of an hour times 2 to see how far they went, right? What is it that they tell me? What is this? These are easy. What are those? What's that? That's dx dt. And that is dq dt. I like it. And they ask me for dz dt. I like it. Kick ass. What does this look like? It's trying to set up here. I know stuff about this side, I know that angle, I know stuff about this side, and I don't know stuff about that side.
I was thinking maybe law of sine and law of cosine.
It's got to be law of cosines because I can't make a complete ratio. Right? Law of sines, you required sine A over A. So you got to make a complete ratio. I don't know anybody's side and its angle at the same time. I don't. So it's got to be law of cosines. The minute I say that, you're like, I'm not in pre-calc anymore. Well, it's called pre-calc for a reason. Look at this. Hey, it's happening in real life. So who remembers law of cosines with z, x, and q?
Z squared equals x squared plus q squared 2xq times, or minus 2xq.
Oh, I see. 2xq. I'm sorry. Q is weird. I was like, cubed? No, cubed.
2xq. Yeah.
Cosine. That's why it's called all cosines. It's crazy. Cosine of, we haven't called it anything yet. But yeah, it's going to have to, it stays 45 degrees, doesn't it? They maintain that. She's going off northeast. It didn't say anything about now. She moves to the, now that would suck. Now she starts going north. No, she doesn't. She's if I wrote that, I want somebody, no, she decided against that, Jeff.
She chose against.
I like that. And yeah, now you take derivatives. And this is why they had to give you 2 rates. I've got 3 variables here, right? This is going to be yummy. What do you have to use over here? Product rule, yeah. Yeah. Sorry. Alright, that's enough. I've got it set up for you. Setup is normally the hardest part. Now you attack this, and you know the rules, you use the rules correctly, you plug in everything you know. At 15 minutes, 1/4 hour, you can figure out what x actually is, you can figure out what q actually is. You could then figure out what z actually is. Because you need z also. And of course, how do you get z? You use the rule you started with, which is something you kind of realized earlier. I'm going to have to put a z in, I'm going to have to put stuff into this formula to figure out what z is after 15 minutes. Do you guys see that? But I'd rather you do that second so you don't get it stuck in your head that you have values and you try to plug them in too early. Because that happens too often. Alright, maybe. Okay. Anything else from homework? Did I skip anybody over?
21.
Oh, yeah. Is this one? Oh, I see. Okay. Holy shit. All right, this is obviously the last question.
I don't have my ID. It's 21.
Oh, healthy. It needs its ID. It wants to get into this club. I feel like I'm in my first apartment. Hey!
We're watching Charlie Brown.
So at noon, ship A is 100 kilometers west of ship B. 100 kilometers west. This is at noon. Ship A is sailing south at 35 kilometers an hour. You're probably going north, aren't you, B? What are you doing, B? Yeah, sailing north, 25 kilometers an hour. Oh, how fast is the distance between the ships changing at 4 p.m.? So then this is some arbitrary position after some time. And so this is the distance I'm really interested in here, right? The distance between them.
Could you extend that up and get another triangle. Extend.
Yeah, now you can do whatever you need to do. So I need a relationship between, in fact, what do I want to call thing? Let me draw this over again here. Let's label what we got here. So we got this going on. I like this. And this is what I'm interested in. So this is 100 here. This, what do we want to call this?
Call it
Yeah, let's call it A. It sounds good. A. So then 35 dA dt is 35. Call this B. So dB dt is 25. Okay, so far. And what do you want to call this?
Z.
Z?
Yes.
Yes, okay, sorry. And so what they're asking me for is dz dt. So I need some kind of relationship between Z, A, and B. I like this. So you could, I like it. So you could either look at these like two little triangles here. That's interesting. Or, like you're saying, you could draw one big triangle here, because then I know what this much is, right?
Yeah.
That is,
35.
no, that's the speed.
Some variable plus A.
Not just some variable.
A plus B.
We've already given, yeah, this is B, isn't it?
Oh.
A plus B.
Right? Thankfully, or else this would be stupid to do. I need to incorporate. Come on. Do you understand? That would be silly to do that if it wasn't related to something I know something about. Why would I bring it in? I would say, screw that. No, but thank God that is B. It's got it. That's the whole reason. And then it would go straight over to make a nice right triangle here, right? And this, of course, would be 100. That's an excellent idea. Or if you already kind of looked at this and you look at the two little triangles, you could do something with those.
Then we could get Z by using.
So yeah, now it feels like a problem we did earlier.
You can't.
Wait, so DZ
Yeah,
is 100?
It says that noon, so it's 4 hours later.
Yeah, 4 hours later, it says 4 p.m.
It's, yeah.
At 4 p.m., what dz equals what? Alright, I'll tell you what, that's enough for that. You guys work on that. I gotta get back into some new stuff. In the 10 minutes I've left. What is it, man? Clock for real? Where time goes to die. You guys probably agree with that statement a little too much. Alright. Alright. So we barely got into section 310 last time. Let's see, how much did we do? We just did like a little tiny bit. It almost seems too good to believe that. Let me just move that over. So we start with something we know. And we say, okay, y is f of x. M is f prime. And this is an approximation. And it's an approximation because this is an equation for what kind of thing? Straight line. This is an approximation because it's approximating this function, it could be anything, with a straight line. So this approximation is only good within some distance from A. At A, it's perfect. What do you get if you plug an A in?
Then it would be equals.
What do you get when you plug an A in? What's f prime of A times A minus A? 0. And you get f of A. Of course, at A, it's built to be perfect because they freaking built that piece in, right? So you want it to be perfect at the center. And as you go a little bit away from A, so your function is doing who knows what kind of weird shit. So here's A. Here's f of A. Shoop. And then here's my tangent line. Let me see if I can do this. That's all the colors you got, Jeff. So the further, if I don't get very far away at all, then that's a pretty good approximation for that. In fact, you're in the back, you're like, you just drew the same damn point. But if I get far away from A, too far away, then that's way too big of a difference, maybe. Depends on how much error tolerance you have. You know, I can tolerate a lot of error, Jeff, in my own work. Learn from me. No. All right. So part of this is how to figure out if somebody gives you an error tolerance, a specific one. It's a very visual thing we can do. That's the basic idea. I mean, this is almost too beautiful to believe. And if you are taking Calc 2, how many guys are taking Calc 2? How many guys were thinking about it and then decided not to after taking some of this? No? Okay, nobody wants to admit that? Okay. What you do in Calc 2 is you take the second derivative and multiply this squared and over 2. You got all this nifty stuff. Just better and better and better approximation. So the best approximation is if you take that out to infinity. And then that shirt that I wear, e to the I pi plus 1 equals 0, once you start talking about that, you can prove that, which is a huge deal, actually. And it's actually, well, if I get some time, I want to show you guys some things that you normally don't get to see about complex numbers. You can see real answers. You can draw a parabola and see the x-intercepts. But if a parabola's up here and you get complex answers, you're like, what the hell? Where's that? Where's that shit? So maybe I'll show you some of that if I get some time. So how do you use this? Well, we did a quick example last time. So if I had, let's say, the cube root of x. So let's do this one all the way out to the point where I can show you on the graphing calculator. Well, let's see. Your thing's too hopeful. Oh, cool. All right. What's that guy's derivative?
1/3.
And just to nip this in the bud a little bit, I've seen a couple people do this. If you just write this, and then write this, and then you write this, it feels like there's nothing wrong with that, but there's so much wrong with that. It's sort of like me writing 5 and then below it writing 10, and then say, oh yeah, I doubled it. You doubled it. You can't just double it. You need to have 2 freaking sides. So if I do something to one side, I also do it to the other side. That's what maintains equality. So you can't have a variable, you can't have this hanging out. Does that, you guys see what I'm saying? So I don't know if you ever noticed, I always have y equals tangent, and then I ask what y prime is, or I just say tangent and what is its derivative. So this is like a simplify this question. Sort of like this would be a simplify this, and then you get 10. Because I've written exactly what I'm doing. You guys kind of see what I'm saying? A little bit, okay. So let's say I want to expand this. What's a good number for cube root?
8.
8. I like 8. I was waiting for somebody to say 0. 0 is really good. Which is not bad. Actually, 0 is good to use. So let's use 8. Let's expand this around 8. So I want it to work perfectly at 8. This linear approximation. So I've got the formula for it. So I need to know what f prime of 8 is. And what's f prime of 8? Cube root of 8 to the negative 2. 1/4 times 1/3. All right, cool. I like it. So that's f prime of 8. What's f of 8? 2. I like it. You see how important it is already to know when to plug into which freaking function, f or f prime? And then we're going to have f double prime. Which one do you plug it into? You got to be careful. So what is f of x approximately equal to? F of x, which is the cube root of x, is actually approximately equal to f prime of a, 1/12, x minus 8 plus 2, which I can clean up a little bit to be 1/12 x minus 2/3 plus 2 is 4/3. Does that sound good? Is it? No. It's plus 2. Yeah. 6/3 minus 2/3 is 4/3. Good job. How are we doing? We alright? Alright, now watch this. This is obviously going to be it for us. So real quick, use what we just did. One thing you can do directly is, since it's a equals 8, I can approximate the cube root of, like for example, 8.03. 2. Because then, if I use this, what's my x value? So f of x, f of 8.03 is approximately equal to 1/12 8.03. So this will be 1/12. Why am I doing that there? Of x, which is 8.03, plus 4/3. Somebody help me out. What is that? You guys cool with that? I'm just plugging it in. F of x at any point is approximated by this linear function. What do you guys get?
2.0025.
2.0025. What is the cube root of 8.03?
2.00249.
Oh man, we're so far off of each other. Pretty good, right? Pretty good. I don't know if you guys really understand it because I'm eternally trying to cram it into the last 7 minutes. But we took a function that is very arguably nowhere near linear, and we approximated it with a linear function. There. And of course, now I used 8.03. Didn't get very far away from 8. If I tried to use 11 here, I would probably not get very close to the right answer.
Is this another way to understand the limits? Or?
Not really, but in a minute it's going to feel like the same stuff we were talking about with limits. But you can use what we're doing now to replace weird functions with linear expressions in limit stuff, and then simplify that. Does that?
Wait, so you want to use equation? Or no, just an approximation?
Well, you have to get this, and then you can use it
Oh,
to
okay.
get the approximation.
Okay.
So that's where I got the 2.0. So if I graph, where am I at? 1/12 x, just 1x, got it, plus 4/3, right? Good job, Jeff. Now, let me see. Oh, I could do this. And 0 minutes. Probably not. So I want this approximation, 1/12 x plus 4/3. I want that to be close to square root of, cube root of x. Right? Near 8. So what I can do is, if I wanted to be within 0.1 of that, let's stay with this. It's kind of interesting. That means the cube root of x minus 0.1 is less than or equal to this. It's less than or equal to the cube root of x plus 0.1. Is that cool? That's within 0.1 of my approximation, right? Oh, did I do it? Right. Yeah, good. You're fine. All right. So now, here we go. With a few of you guys that are left. X to the 1/3. Just 1/3 there. Minus 0.1. Oh my God. Is there a cube root? Yes. Cube root of x. Plus 0.1. Of course, I want around 8. So there's the linear approximation. Here comes the cube root. That's the bottom cube root. And here comes the top cube root. You can't see much of shit, right? Because they're pretty close. How far apart are those two? 0.2, right? So if I zoom in, see the next class is getting all antsy. You guys are getting all antsy. Jeff's just trying to do his job. Alright, so here I am close to 8. There's the linear approximation. Here comes the cube root. That's minus 0.1, and here's plus 0.1, right? So what we want to do is we want to see, if I zoom out a little bit, I can see where my linear approximation hits the top or the bottom. If it hits and goes through, it's going to be outside of that 0.1 tolerance. All right. I tried to cram as much as I could. And you didn't see any of that. It's too bad. You still don't see any of that.
So quiz tomorrow,
Quiz tomorrow is related rates. Yeah, 3-9. 3-9.